For this question, we need, as it says, to find a counterexample. Now, since we're dealing with prime numbers and there is no rule for generating prime numbers, then the best thing we can do is start with the first prime number and work our way up until we find a counterexample. It would be unreasonable to use a huge prime number in this situation because there's no method for discovering how to get to it. So it's going to be a smallish one and we're just going to check through. So if we start with p is 2, then p squared plus p plus 1 will be 2 squared plus 2 plus 1, and that is 7, which is prime. So this is why Hugh thinks that it might be a rule. Anyway, we'll try the next one. 3 squared plus 3 plus 1, which is 13, still prime. With 5, we have 5 squared plus 5 plus 1, which is 31. So it's looking good for Hugh at this stage. But sadly, Hugh didn't go that one step further and get 57. And we know that 57 divides by 3. And we'll have a little look at how we know that later. But for the moment, that is in fact 3 times 19, therefore is not prime, and there is our counterexample. And we would write a statement to say that's the counterexample to round the question off. Now I mentioned that we can tell that 57 divides by 3, and this may be a rule that you know, or it may not, but the rule is that if the digits of a number add up to a multiple of 3, then the number itself is a multiple of 3. And that's true for 9 as well. If we add up the digits of a number and that divides by 9, then the original number divides by 9. And it's a nice little proof of that. And it goes like this. If we think of a number with 5 digits, so say we have A, B, C, D, E, then in this number, E is in the units column, so that is just E. D is in the tens column, so actually it stands for 10 lots of D, and then C stands for 100 lots of C, B for 1,000 lots of B, and A for 10,000 lots of A. Now, this is the clever little bit, is that we now separate this off. So we have our E, and then we have D plus 9D. We have C plus 99C, B plus 999B, and A plus 9,999A. So just writing this the other way round, A plus B plus C plus D plus E plus 9 times 1,111 A's, 111 B's, 11 C, and a D. And now we can see where the rule comes from, because for the right hand side of this equation, the part that has a multiple of 9 here, that must divide by 9 and also must divide by 3. So if this part, if that divides by 9, that tells us that the whole thing divides by 9. And if it divides by 3, that tells us the whole thing divides by 3. So we could test this with a number, so we'll try the number 13,701. So if we add the digits together, 1 plus 3 plus 7 plus 0 plus 1, that gives us 12, and then if we add those together, 1 plus 2 is 3. So this tells us that this number divides by 3, but because the digit sum didn't end up as 9, it won't divide by 9. So let's check that. 13,701 divided by 3 comes to 4,567, but 13,701 divided by 9 comes to 1,522 and a third. So it doesn't divide by 9. Now this is a question about proof, obviously, and proof is at the heart of mathematics. And it's the first thing mentioned on both the AS syllabus and on the A2 syllabus. So you'll have looked at A, B and C, the proof by deduction, exhaustion and disproof by counterexample. But we'll just have a little look at proof by contradiction, which is what comes up for you next when you start your A2. One of the proofs that's actually mentioned in the syllabus that you have to know is the infinity of primes. And this is a really important matter. Prime numbers, as I'm sure you already know, are the building blocks for all numbers. And so they're really, really important. Now, if you think about the prime numbers, why should there be an infinity of them? You might think once they get really huge, we get to a point where there was always something that divided into it. So perhaps the prime numbers would run out. On the other hand, you might just think, well, why wouldn't they go on forever? The whole point is, in mathematics, it's not about what we might think, it's about proving things. It's also a really interesting proof because we know that Euclid in 300 BC knew this proof. Whether he was the first or not, we don't know, but it's a very ancient matter. Now, just for notation, we're going to use this symbol to mean the set of prime numbers. And that fits in with the fact that we use this for the natural numbers, and this stands for Zahlen in German, which is the set of integers. Etc. So our theorem is that the set P has a size of, so we can use the modulus sign, infinity. And we start the proof by assuming the opposite. So we say that the set of primes is not infinite. And this means that there must be a biggest prime. So we'll call this biggest prime P. And now we make a number by multiplying all the prime numbers up to P together. Okay, so our new number, which we'll call Q, is equal to 2 times 3 times 5 times 7, all the way up to P. And then, this is the clever trick, we add 1. Now, either Q is a prime number, or Q is not a prime number. If Q is a prime number, then since Q must be bigger than P, we have a contradiction, because we've already said that P is the biggest prime number. And the symbol, or one of the symbols for contradiction, is this. So we have a contradiction. So that then tells us, because all our steps are correct, so everything's correct and okay, from this assumption, then this assumption is false, and then that tells us that this must be true. So let's look at the case where Q itself is not a prime number. Well, this tells us that there must be a number less than or equal to p that divides into q. Because p is the largest prime number, then any number that does divide into q must be less than or equal to p. But if we try to divide by the prime numbers up to p, then we can see what happens. So if we do q divided by 2, then that will give us 3 times 5 times 7 all the way up to p. And notice the 2's disappeared because it's cancelled. In fact, I'll just put it in. But we've also got this 1 that has to be divided by 2. So here we have a whole number here, but then we have a half. So q doesn't divide by 2. So what about 3? Well, this time if we divide by 3, then the 3 cancels there. So again, we have a whole number here, but we have an extra third. So q doesn't divide by 3. And we can carry on this process until we test p itself. And this time, p will cancel, but we'll be left with a whole number here, but there's still this extra little bit, which means that q doesn't divide by p. Now we said that q was not a prime number, but we've shown that if our original assumption were true, then it would divide by a prime number smaller than or equal to p, and we've shown that it doesn't. So we have a contradiction. So again, the contradiction came from, because all these steps, following this green line up, all these steps are okay until we get to here. So that must be false, which tells us that this is true. And that's the proof of the infinitude of prime numbers.